And so last time we had been talking about the eigenstates of a general angular momentum operator. J. Okay, and let's write them out just for review. So we said that the operator J squared acting on an eigenstate with a redundancy label that I'm going to call N today for variety. Last time we called it K, is H bar squared, not J squared, but J times J plus 1 times the same state. J sub z acting on this eigenstate is H bar times M. And then there were the operators J plus and J minus, and they don't commute with J sub z. So instead of getting eigenstates, they raise or lower M. And the factor here turns out to be H bar square root of J times J plus 1 minus M times M plus 1 times the state with M raised by 1 unit. And J minus looks very similar. So it's J times J plus 1 again, but now it's minus M times M minus 1 with M lowered by 1 unit. Okay, and so from the last two, you can get Jx, because that's, well, Jx and Jy, because they are linear combinations of J plus and J minus. And again, N here is a redundancy label from the point of view of angular momentum. And so this is typically the eigenvalue of some other operator, most usually the Hamiltonian. But in principle, it could be some other operator or operators that formed a complete set of commuting observables with the angular momentum operators, J squared and J sub z. And so last time, what we had started to do was to look at matrix representations for these operators. And so what that means is we're going to have states. I'm going to just drop the redundancy label because it does absolutely nothing in any of this. So the states are represented by vectors in an ortho basis. So they're orthogonal and they form a basis. And then the operators that we're talking about here, Jx, Jy, Jz, from which you can form J plus and J minus and J squared. All of these are represented by matrices. So you can read the double arrow notation as represented by. And so last time we'd worked out the first two ones. There's J equals 0, which is a 1 by 1 matrix where everything is all zeros. So Jx, Jy, Jz, J plus, J minus. These are all 0. J squared is 0. Then there was the J equals 1/2 case, the spin 1/2 case, where everything is a 2 by 2 matrix. And then the vectors in the Hilbert space, there I'm writing it as a JM notation, but I can write it as a up arrow. And this is corresponding to or represented in the Hilbert space by the vector 1, 0. 1/2 minus 1/2 in JM notation is spin down, and that's represented by 0, 1. And then we said that J The operator is represented by the matrix h bar over 2 times the sigma matrices, or the Pauli matrices. Okay, and j squared is represented by h bar squared times 3/4, 1, 0, 0, 1. Okay, so now let's graduate to the case of j equals 1. So we're looking at a j equals 1 subspace. Whatever our physical theory is, it may have other values of j as well, but we're just restricting to this one subspace. And then an orthobasis for a given n. So for each n, that means we're fixing n, we can write as 1, 1, and 1, 0, and 1, minus 1. That's our JM notation. Okay, and then we're going to represent these by vectors, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, and then we can work out the matrix representation for all of our J operators. So the easy ones are the ones for which these are eigenvectors. For example, we know that J squared is going to be diagonal because when it acts on each one of these vectors, it's just going to give back a number. Okay, and so it's represented on these things by a diagonal matrix, which is going to be 2 h bar squared, 1, 0, 0, 0, 0, 0, 0, 0, 1. Okay, the 2 here comes because that's j times j plus 1. So it's 1 times 2. So that's where that comes from. And j sub z is equal to just h bar times 1, 0, 0, 0, 0, 0, 0, 0, minus 1. Because in each case, the entries on the diagonal are the eigenvalues. Right? So it's Monday morning. Where did I screw up? You can tell me which thing I got wrong here. Nobody? So this was wrong. This 0 should have been a 1. So let's fix that. Because all of these states have the same eigenvalue of j squared. It's j times j plus 1 times h bar squared. So these should have each been just 2 h bar squared. The 2 h bar squared I've pulled out front, but otherwise it's just the identity matrix, whereas j sub z is giving the first number, which is the same, and j sub z is giving the second number, which is 1, 0, or minus 1. Okay, so now let's work out what the matrices for J plus are. Okay, and so the strategy for doing this is just to figure out, first of all, how it acts on each of the orthobasis kets, and then translate that into matrix notation. So first, J plus acting on 1, 1 is equal to the null ket, because once I have the highest value of m that I can possibly have, and I try to raise it again, I get nothing. And so what that tells us is that the first column of the matrix J plus is going to be all zeros. Okay, J plus acting on 1, 0 is a little more interesting. This is h bar, and then we go back to our general formula, which says this is 1 times 2 minus 0 times 1. And it's giving back the state 1, 1. Actually, I made another mistake here. This should have been, all of these states have j equals 1. So the first entry is always 1. Okay, and so this is equal to square root of 2 h bar, 1, 1. And what that tells us is that the second column of this matrix is square root of 2 h bar, 0, 0. Okay, that's telling you that when you act on when you act on the second ket here, the first entry is square root of 2 h bar. That's for the 1, 1. And the other ones aren't there, so they give zeros. Okay, and then finally we have j plus 1 minus 1. And again, you plug into the formula. The first term is always the same. It's 1 times 2. But now it's minus negative 1 times 0, acting on 1, 0. So that's square root of 2 h bar, 1, 0. Okay, and that tells us that the third column of this matrix is 0 square root of 2 h bar, 0. Okay, and the way that works is, again, because now when we act on the third of the basis kets, the only thing that's non-zero is it gives something proportional to the second one. That's why it's the middle entry here. And it's equal to square root of 2 h bar. So that's the actual value. Okay, and so we can put all of that together. And that says the operator j plus is represented by the matrix square root of 2 h bar times 0, 1, 0, 0, 0, 1, 0, 0, 0. We're just putting together the columns that we found before. Okay, and then similarly, I'm not going to go through the arithmetic because it's almost the identical thing. J minus is represented by square root of 2 h bar. It's just that now the non-zero entries come in different places. So it's 0, 0, 0, 1, 0, 0, 0, 1, 0. And then once we have j plus and j minus, then we can get jx, because jx is 1/2 j plus plus j minus. So that's telling us this is represented by h bar over the square root of 2 times the matrix 0, 1, 0, 1, 0, 1, 0, 1, 0. And similarly, j minus is 1 over 2i, j plus plus j minus. So that's represented by h bar over square root of 2, 0 minus I, 0, I, 0 minus I, 0, I, 0. Okay, so by doing this, by just looking at each action of j plus and j minus acting on our kets, we can figure out what the matrices are, and then from the matrices we can get jx and jy from the relation between j plus and j minus and them. Okay, so we've basically worked out everything there is to know about how the j operators act as matrices on the j equals 1 states, if in fact there are j equals 1 states. But again, whether there are j equals 1 states or what their role is depends on the physical situation. But the nice thing about all of these is that you can work it out once, and then the answers don't depend on what the physical situation is or what the physical system is. Okay, so we've done j equals 0, j equals 1/2, j equals 1. And now we can talk about arbitrary j, since we've seen how this works. So suppose our Hilbert space has an arbitrary j subspace. Okay, and so the orthobasis for this has 2j plus 1 states, because those correspond to the possible values of m. M equals minus j up to plus j. Okay, and so the states are labeled, the first entry is always j, and then the second entry is always m, so that's the list of them. And now we can work out what the representation of j squared is. It's represented by j times j plus 1 times h bar squared times the identity matrix. So it's all ones on the diagonal. And it's all zeros everywhere else, which I'm just going to write by drawing zeros off the diagonal like that. Okay, and j sub z is h bar. And now on the diagonal, we just put down the eigenvalues, which are j minus 1, all the way down to minus j. And again, these are diagonal matrices, so there's zeros everywhere off the diagonal. Okay, now j plus and j minus are a little bit harder, but one can do the same strategy that we did up here. Okay, we just figure out how they act on each one of the basis kets in turn. There are 2j plus 1 of those. And those are going to be the 2j plus 1 columns of the matrix representing j plus or j minus. Okay, so I'm going to skip that step and say once you've done that, then you can assemble jx. And so here are the matrix elements of jx. So if I take the matrix for jx and I look at the m prime entry, this is going to be h bar over 2. And then there are going to be square roots, j times j plus 1 plus m times m plus 1, delta m minus 1, plus square root j plus 1 minus m minus 1, delta m prime plus 1. Okay, and so the first term is really coming from the j plus, and this whole term is coming from j minus, and we've pulled out a factor of h bar. And then the 1/2 is because there's a 1/2 in the definition of jx from j plus and j minus. And then I can write a similar thing for j sub y. These are the matrix elements. And so there's an I factor here. But otherwise, it looks almost identical with the Kronecker deltas and everything. The only difference is there's a minus sign here. Okay, so the plus turns into a minus. And we get this extra factor of I for j sub y. So if we wanted to sort of draw schematically what these matrices look like, oops, I got a black again. J sub x is going to be represented by a matrix that has an h bar. And then the Kronecker deltas here are telling you that it's non-zero if and only if you're one above or one below the diagonal. And so I'm just going to draw here the places where there are non-zero entries. So there's one, there's one, there's one, there's one, there's one, there's one, all the way down to here. Okay, and there are zeros actually on the diagonal. Okay, and then everywhere more than one unit off the diagonal is also zeros. So that's what J sub x looks like. And then J sub y is going to have an I. By the way, the blue dots represent real numbers, real positive numbers that come from square roots. So maybe I should say that. Real positive square roots of stuff. And J sub y looks like this. So again, I'm going to put in the zeros on the diagonal because the Kronecker delta says from up here says that it's always zero on the diagonal because m is and m prime. This should have been m prime here. If m and m prime are equal, then you get no contribution. And then off the diagonal, the blue dots again are where you can have non-zero entries, except that there has to be a minus sign in front of the the one that's higher. Okay, and so that's the schematic form of what these matrices look like. And then if you're worried about a particular J, then you have to do some square rooting to find out what the blue dots are specifically. Right now, they just represent the possible non-zero entries in the matrices. Okay, so now that we have the J operators and their representations, we can talk about the generators of rotations. So generators or generator of rotations. These are unitary operators that do a change of basis corresponding to a rotation. Okay, and so this is for a rotation by an angle alpha, which is going to be a magnitude times a direction. This is n hat is the axis of rotation of whatever transformation you're doing. And we write it like this: u of alpha is equal to the exponential of minus I alpha dot j. This should have been a vector. Divided by h bar. All right, so one thing that's useful to note about this is that when we look at this operator on the right-hand side, this operator just ignores the redundancy label n. It never changes the redundancy label n. And in fact, it also ignores j. And the only thing it does, if you look at these matrices, is it possibly mixes up, here and here, it possibly mixes up what the m values are. Okay, so this operator mixes m's, but never changes the values of n or j. They just stay the same. So what that means is we can work with a fixed j subspace. Especially if we're working in the matrix representation. Okay, and it's traditional to call these unitary matrices D for some reason I don't know. So traditional to call, oops, U of alpha as D, and then it's got a little label on it, J, to tell you what J subspace you're working in. Okay, and so once again, we can do this once and for all and apply it to any physical situation for different values of J. For small j, we can actually do the exponential series in general. Doing the exponential of an operator is going to be a little bit tricky, but for small j, we can do it. So for example, the easiest case, of course, is for j equals 0. For j equals 0, basically what we're doing here is we're taking an exponential of something that's always 0. And so that's 1, or the identity operator. Okay, so dj, the unitary operator that does rotations, is e to the 0, which is equal to 1. So that's another way of saying if you're in a j equals 0 state, doing a rotation doesn't change your state. It just leaves it the same. Okay, for j equals 1/2, things are a little bit more interesting. So now we're asking for, so this, I guess I should have been more specific and called this d of 0. Now we're asking for d 1/2, which is the exponential of minus I alpha dot j over h bar. But we know what that is for j equals 1/2. This is the same thing as the Pauli matrices. So it's minus I theta dot sigma divided by 2. And now let's just write out the whole series. This is the exponential series is 1 minus I theta. Oops, I didn't mean theta, I meant alpha. Okay, so this should have been alpha. So it's alpha dot sigma over 2 plus 1/2 minus I alpha dot sigma over 2 squared plus 1 over 3 factorial minus I alpha dot sigma over 2 cubed plus 1 over 4 factorial minus I alpha dot sigma over 2 to the 4th, going on forever and ever. So that looks hard, but now we can use the fact that we ended last time with, and that is if we take alpha dot sigma over 2 and we square it, that's equal to the magnitude of alpha over 2 squared times the identity. So when I write 1 here, that's really the 2 by 2 identity matrix. Okay, so what that means is every time I have more than 2 powers of this quantity in the sum, I can just replace it by something times the identity. And so, for example, this term is going to be just proportional to the identity. This term is going to be proportional to the first term, or this term, because 2 of them turn into the identity, and then 1's left over. This one's going to be proportional to this squared. Okay, and so when we add this all up, d 1/2, I guess I should write d 1/2 as a function of alpha. There are going to be 2 sorts of terms. They're going to be ones proportional to the 2 by 2 identity matrix. And what goes here is 1 minus 1 over 2 factorial alpha over 2 squared plus 1 over 4 factorial alpha over 2 to the 4th plus basically all the even terms in the series. And then there are going to be terms that look like minus I n hat dot sigma times alpha over 2 minus 1 over 3 factorial alpha over 2 cubed plus 1 over 5 factorial alpha over 2 to the 5th, going on forever and ever. Okay, and notice that when we did this, there was a factor of I that comes in here, and that flips the sign of every other term. So that's why there's a minus sign here and a minus sign here. And now we can recognize this as the cosine series, and this is the sine series. And so we can put this together as cosine alpha over 2 times the 2 by 2 identity matrix minus I n hat dot sigma, the Pauli matrix, times sine alpha over 2. Okay, and so this is d1/2 of alpha. And this equation is telling you, if you've got a spin 1/2 system, how do you rotate it by any angle that you want about any axis that you want? Okay, so this rotates a spin 1/2 system state about the axis n hat by the angle with magnitude alpha, where alpha, the vector, is equal to its magnitude times its axis. So spin 1/2 is kind of special in this way because you can sum up the infinite series in this way. It's not so easy for any other values of j. So what you have to do for larger values of j is you often have to worry about specific angles. And you can have your computers do the sum for you because it's just some matrix algebra, and computers are really good at that. But say, for example, that we wanted j equals 1. And let's say we were only interested in rotations about the z-axis. So that's the other case where it's easy to do. Anything with rotations about the z-axis is special. And so if we're interested in the d operator, the unitary operator for alpha times z hat, that's equal to the exponential of minus I alpha dot j over h bar. That's the general formula, which is equal in this case to exponential minus I alpha magnitude j sub z divided by h bar. And now we know what j sub z's representation is. So this is the exponential of minus I alpha 1 0 0 0 0 0 0 0 minus 1. Notice the h bar has canceled out because there was an h bar in the representation of j sub z. Okay, and the nice thing about diagonal matrices is they're super easy to exponentiate because you just exponentiate the things on the diagonal. So diagonal matrices, easy. Okay, and so in this particular case, the answer is just this matrix, e to the minus I alpha 0 and e to the plus I alpha on the diagonal. Okay, and so that's the matrix that is telling you how to rotate about the z-axis for a j=1 system. You just multiply by phases, and once again, I put a 0 where I meant a 1. Right here, this should have been a 1. Because when I exponentiate 0, I get 1, not 0. Okay, let's do a harder case, a harder example. So this would be a case where we're going to rotate in a spin 1 system or a j=1/2 system, but about the x-axis. Okay, so that's our angle. And this is equal to the exponential of minus I alpha j sub x over h bar. And the problem is this is not diagonal. So how are we going to exponentiate that? For the Pauli matrix case with j=1/2, we were lucky because we had a special relationship. And a similar thing happens here, it's just more complicated. So fortunately, if you start taking powers of j sub x, you discover that the terms in the series start to repeat because they come in multiples of j sub x. And specifically, they're in multiples of j sub x over h bar to the pth power for only 3 values of p, namely p = 0, 1, and 2. So once you get to 3 powers of p, then it's proportional to the identity. When you get to 4 powers of p, it's proportional to this to the first power, etc. And if you work all the combinatorics out, you discover that d1 of alpha x hat is the identity minus I sine alpha times jx over h bar plus cosine alpha minus 1 times jx over h bar squared. Okay, and jx over h bar is just this thing, 0, 1, 1, 0, 0, 1, 1, 0. Okay, and that's it. The whole series, the whole infinite series sums up into a thing that you can write in just 3 terms. Okay, but then if you're doing something like j = 2 and around some arbitrary axis that's pointing in some arbitrary direction, then things get a little bit more complicated and you sort of have to deal with it on a case-by-case basis. Okay, any questions on what we've done so far?
Professor, what section of the notes is this on?
We've been going through chapter 7. So yeah, sorry, I did a little skipping around. So we had gone back to section 4, chapter 4 for a little bit, but now we're in section 7.4 and 7.5.
Okay.
Just actually finished 7.5 and we're about to start talking about 7.6.
Okay.
But for variety, I'm doing things in slightly different order than the notes, and I think a little bit of variety is not a bad thing.
Thank you.
Okay, so in fact, the next topic here is going to be, we're going to go back to orbital angular momentum, and we're going to work out its representation in the spherical coordinate representation. So this is an alternative to the matrix representation, which is often very useful. So what that means is we're working in a position basis. We have some position eigenstates. And then the wave function for our system, which is a function of x, y, z, is equal to XYZ. By the way, this is a synonym. XYZ is a synonym for R. Okay, but we could also write that in spherical coordinates. In fact, we will. So then that's equal to the bra R theta phi acting on psi. And here's where we're going to take advantage of the tensor product idea and write this as a bra for R, tensor product with a bra for theta phi. I'm just splitting those two things up, acting on psi. Okay, and so really, I haven't really done anything deep here. I've just taken this bra and separated into a tensor product where there's an R part and a theta phi part separately. But where this will lead is, so I'm going to say we'll find okay, that for an eigenket NLM, that the wave function for that eigenket as a function of the spherical coordinates is going to equal, again, it's R cross theta phi acting on NLM, which is going to be a function of R only, which is going to carry the N label, and a function of theta and phi only, which is we're going to call by tradition YLM. Okay, and so those things are going to be the spherical harmonics, and our job is to figure out what they are. Okay, so we're basically solving an eigenvalue problem, and so we have operators like L sub x, which is y p sub z, minus z p sub y. And then in position representation, that's equal to, actually, let me go back here. This is minus I h bar, y partial z, that's the z momentum, minus z partial y, that's the y momentum. But what we want to do is we want to transfer everything to spherical coordinates. So change to spherical coordinates. Okay, and in my notations, these are defined by x equals r sine theta cosine phi, y equals r sine theta sine phi, and z equals r cosine theta. Okay, and then we're going to need derivatives, things like partial x is partial r, partial x, partial r. Basically, we're using the chain rule here. Oops. Okay, etc. for y and z also. And so if you just take our expressions for L sub x, for example, and the similar ones for L sub y and L sub z, and do all these transformations of differential operators acting on them, what you find is that L sub z is represented by minus I h bar partial phi, which is very nice and simple. Okay, and L plus is represented by plus h bar e to the I phi partial theta plus or minus, or sorry, just plus I cosine theta over sine theta. I'm resisting the temptation to write cotangent theta. In my opinion, cotangent is a highly overrated operator. Okay, and L minus is the same thing, except with various minus signs. But otherwise it's identical. Okay, so now we have LZ, L plus, and L minus, and from these, if you want, you can get Lx and Ly. But also you can put it together and get L squared. This is minus h bar squared, 1 over sine theta, partial theta, acting on sine theta, partial theta, plus 1 over sine squared theta, 2 derivatives with respect to phi. For future reference, it's going to be very useful that this is actually equal to minus h bar squared r squared times the Laplacian operator, plus terms that we'll worry about later that only involve r derivatives. So from our present point of view, we don't have to worry very much about those because we're going to separate things out and we're basically only going to find the part that only depends on theta and phi. Okay, so now we want to solve the eigenvalue problem for these. Okay, and we'll start with L sub z. And so now, going back to our expression for L sub z up here, the equation that we're trying to solve is minus I h bar partial phi. That's the representation of L sub z acting on our wave function. We're aided by the fact that we already know from our general discussion what the eigenvalues are, namely m h bar times psi. Okay, and that's an easy equation to solve. That says that psi has to equal e to the I m phi times a quantity I'm going to call u, which can depend on r and theta, but not on phi. Okay, so that's just working with L sub z. And now let's figure out how these things work for other values of, or the other operators. So if we start with m equals L and act with our raising operator, we should get 0. So that means L plus acting on a ket n L and m equals L equals 0. That's telling us, because we have a representation for L sub plus, that partial theta plus I, I'm still resisting the temptation to write cotangent, all of this acting on e to the I L phi, I've plugged in m equals L, times the unknown function ULL, that should equal 0. Now here's the key trick that we're going to use. We're going to use the fact that here we already know what partial phi does acting on this. Namely, it just brings down a factor of I times L. That really came from this equation up here. Okay, and so we can just replace partial theta by I times L. And so we get partial theta minus L cosine theta over sine theta e to the I L phi ULL equals 0. But now the nice thing is I don't have any more derivatives or phi's involved except this one multiplicative factor here. And because the whole thing's supposed to be equal to 0, I can just cross that out. and rewrite the equation as d by d theta acting on ULL equals L cos theta over sine theta ULL. Okay, and now I can rewrite that by rearranging the differentials. Okay, and now the right-hand side, this is nicely proportional to d sine theta over sine theta, which is otherwise known as the differential of the logarithm of sine theta. Okay, and the left-hand side is the differential of logarithm of ULL. And so now we can exponentiate both sides, or integrate both sides. Okay, and so what we get is ULL is equal to sine theta to the nth power times the exponential of a constant of integration. So this is some constant with respect to theta and phi, but it could be a function of r. Okay, and so finally, we've got ULL is equal to some function of r, which by the way can also depend on what n is, times sine theta to the nth power. All right, and so finally putting everything together, our wave function psi NLL of r, theta, and phi is a function of r only as promised before, times YLL, which we're now defining. Okay, and YLL, theta phi, we are defining to be a phase factor that's really pretty arbitrary. In fact, not all books use the same phase factor. And then there's a normalization factor that I'll explain next time where this comes from. It's basically by requiring this to be a unit norm thing. It's kind of a complicated phase normalization factor. But then the rest of it, the part that actually depends on theta and phi, is relatively simple. It's sine theta to the L, e to the I L phi. Okay, so this is a normalization. We'll do that next time. And this is an arbitrary phase that depends on what book you're reading. But I've chosen one particular very common phase convention known as the Condon-Shortley phase convention. All right, so that's it for today. Oops, sorry, I went a little bit over. But we'll talk more about the spherical harmonics and how they are related to angular momentum next time. So you all should have got an email from me reminding you that a week from today is our second midterm. Our second midterm, my plan is to have it be extremely focused and therefore hopefully easier to study for. Basically, what we've done in the meantime has been mostly the harmonic oscillator. And so your job to study for that is to learn the harmonic oscillator in all of its aspects. That means coherent states, energy eigenvalues, the algebraic representation, and we've had for homework and in class the one-dimensional, two-dimensional, and three-dimensional harmonic oscillators and how they work. Okay, so hopefully that should give you a clue as to what to expect on the second midterm. Okay, any questions?
I have a question from the notes, if no one else has questions.
Okay. Anybody else have a question specifically about the lecture today? No? Okay, let me turn off the recording then.